Alright, my name is Daniel Yoon, and my research advisor is Dr. Shin Jae-hyun. And my research topic is computational and experimental measurement of inhaled aerosol deposition in simplified pharmaceutical dry model and new moist and temperature controlled mouth-throat airway models. Let's start with some background and introduction. Inhaled aerosol deposition studies of human respiratory system allow health professionals to gain an insight between the aerosol particulate matters and the exposed surfaces of the lung airways. Especially the pharmaceutical companies and pulmonologists find these studies very useful, developing more efficient drug delivery system or assessing the effective dosage for their patients. Numerous studies have been conducted both in vivo and in vitro regarding various characteristics of human respiratory system. However, since there are many restrictions and limitations finding human subject or finding an appropriate experimental setting for in vivo studies, most of the aerosol deposition studies have been conducted with in vitro setting. Therefore, finding an accurate and realistic model of human respiratory system has been the most important factor in designing an aerosol inhalation studies. Also, the importance of computational analysis has been more significant since it can not only verify the in vitro experimental data, but also by itself it can predict particle deposition without having an actual experiment. So this model shown on the right is a pharmaceutical model. It is a standardized upper respiratory tract model used by most of the pharmaceutical companies for their research. This model is divided into oral cavity, oropharynx, laryngopharynx, and larynx. And as you can see, it is very different from the real human anatomy of the upper respiratory tract. It is because this model was made not based on a real geometry of human upper respiratory system, but only based on a volumetric ratio of each part. And that was why I studied the difference between this pharmaceutical model and the subject-specific model that was made using a series of CT scan images of a human subject for previous research. And in conclusion for this research, there was a significant difference in particle deposition between these two models. However, it was understandable that developing a standardized model with realistic geometry is almost impossible for pharmaceutical companies, since every person has a different geometry of their respiratory tract. So for this time, using the exact same geometry of the pharmaceutical model, a new moist and temperature controlled model was made to investigate the effect and the importance of humidity and temperature for medicinal aerosol delivery. The first picture shown on the left is again, it's the simple dry model, the standardized pharmaceutical model. Although the pictures are not scaled the same, but they have the same inner dimension with the exact same geometry. And same as previous research, the model on the left, the simple dry model, was printed using a 3D printer. And the second picture shown on the right is the moist temperature model. This model was made from a polyurethane foam to hold the moisture within the model, and the outside shell was used to keep the overall geometry and to keep the sensors of the active temperature control device at their right places. So for experimental method, particles of 0.1% fluorescent and 0.4% oleic acid were suspended in a solution composed of 400 cc of alcohol and 100 cc of DI water. And this solution was used to generate liquid micron-sized aerosol through the vibrating orifice aerosol generator. The average generated particle sizes were from 4.5 to 7 micrometers, and the airflow rates studied were from 15 to 60 liters per minute, which represent from the rest to heavy exercise state. And for the wet model, the urethane foam was soaked in DI water to maintain its humidity, and the average temperature at the wall was maintained at 37 degrees Celsius using this active temperature control device. And this device was designed 2 years ago by one of the senior design team at Mercer. This shows the overall experimental system setup. The liquid micron-sized aerosols with fluorescence were generated with a VOAG, vibrating orifice aerosol generator. Then the particles were passed through the krypton 85 neutralizer to minimize the interactions between the particles. And the particles that were not deposited within the model were collected at the end of the model on a micron-sized filter. And the overall the flow rate of the aerosol particles were controlled using this rotometer, which is placed between the model and a vacuum pump. For the computational fluid dynamics and simulation, ANSYS CFX was used to calculate the airflow, aerosol transport, and aerosol deposition within the model. The exact same model was used, and for each flow conditions, the transport and deposition of 5 different aerosol particles were studied, which are 1, 3, 5, 7, and 10 micrometers. And this shows the 3 main equations we use for our research. The first one is the equation for the aerosol size to compare the experimental aerosol size to the reading from the particle spectrometer. And the second equation is the deposition fraction to compare how much in percent deposited over certain region. And the third one is Stokes number. Stokes numbers is a dimensionless number corresponding to the behavior of the particles suspended in a fluid flow. This deposition fraction versus Stokes number graphs shows the correlation between the experimental data and the computational data. The deposition fraction data for the dry model was found to have a very similar pattern compared to the computational data. And this graph is deposition fraction versus flow rate for those 2 dry model and moist temperature model. As shown on the graph, deposition fraction of 2 models at 15 liters per minute was only 0.5% difference, most likely due to their similar inertial condition. However, at 30, 45, and 60 liters per minute, 31.5, 35.5, and 21.3% difference were found. Such a pattern was expected since the effect of particle inertia is the greatest around 30 to 45 liters per minute. And this may indicate a gradual decreasing deposition pattern as the flow rate increases due to decreasing interaction between the aerosol particles, the wet airway surfaces, and the moisture in the air. Although more accurate computational modeling and simulation techniques are required, the computational modeling and simulation we have created may be used as an effective tool in predicting the aerosol particle deposition within a dry model. As we saw on the last graph, an average of 22.2% more deposition was found within the moist temperature model. And such a result may suggest that any experimentally developed medicinal aerosols using in vitro the dry pharmaceutical model would actually result in a less aerosol deposition, no, more aerosol deposition within the human respiratory system, resulting in a less efficient delivery of the medicinal aerosol to the lung, which is the main target of the pharmaceutical aerosol delivery. For future work, now we have a wide range spectrometer that can measure the diameter of the particles from 0.01 micrometer to 10 micrometer, and a digital fluorometer that gives an absolute absorbance value. These devices have been used for all of our current studies to achieve more accurate data. And for my senior design team's project, we have made an inhalation apparatus that can provide a cyclic airflow to mimic human breathing pattern. This device can not only control the speed, the volumetric flow rate, but also can control the pressure inside of the main pump system. And this can provide various flow rate with various breathing patterns. And this will be used over this coming summer to investigate the effect of cyclic airflow, the cyclic breathing pattern, which is one of the most important characteristics of human respiratory system. And I would like to thank Dr. Jin Jae-hyun and Dr. McCranor for support and advice. Any questions?
I just want to make sure I understand this correctly. You were comparing the dry model to this new humidity and temperature model, and you found that the dry model actually predicted less deposition than was actually happening?
There was less deposition within the dry model, yes.
Which, did you find that the humid model fit better with the actual human test data, or I'm not sure which one was the one
compared to the real human
yeah.
data? Yes, the moist temperature model was much closer to
Okay.
the real data. Okay.
What is the Stokes number?
As I said, it tells you the characteristic of the particle in a fluid flow, with the particle density, particle diameter, mean flow velocity, absolute viscosity of air, diameter of the inlet tube taken into account. Basically, if the Stokes number is high, that means the particle is under the influence of inertia. While if it has a low Stokes number, sorry, let me put it this way. So if it has a high Stokes number, it's highly predicted to follow the initial trajectory of the aerosol. While if you have a low Stokes number, it will just follow the streamline, no matter what the initial trajectory was.
Isn't it a ratio of two forces, like the ratio of the inertial force to
Yes.
the shear force? Is that right?
Mm-hmm.
I liked your last slide. I'm a
question slide?
Futurama fan with Brian. I steal that for my my ending slide. That's great. What has been your biggest thing you've learned doing this project?
That the pharmaceutical companies are using a wrong model.
Have you seen Andrew Weems' presentation about the finger joint?
No, I have not.
He's a graduating honor student, and the current finger joint that they use if they have to replace a knuckle is basically like a silicone tube. And while your finger can do
The
this,
sliding.
yeah, well, no, it just sort of bends like a hinge is what they do now. And while it looks like it's functional, you don't have any grip strength. It'll dislocate it if you try to grab it all. So he came up with a two-face thing, and you would actually have a functional finger now. So it's interesting that you guys are, at your level, determining what, supposedly the powers that be don't know, which is good. So thank you very much.